Benyamini from Weizmann Institute of Science will talk about complex cells and preparation theorems.
Hi, thanks very much for the invitation. I cut my air conditioning because it's kind of loud. Yeah, thanks. This talk is going to be kind of half formal and half conjectural stuff. So I tried to talk about complex cells theory a few times, and it wasn't very successful because there are many details. So I'll try not to give completely accurate formulations, but rather try to motivate it. So let me start with, and feel free to interrupt me. Okay, so I'll start with just the preparation theorems. So preparation theorems, and well, I'll talk about the globally subanalytic one. There are many other kinds, but this is the one we'll focus on. I have a bit to say about other preparation theorems toward the end, maybe. Okay, so what is a preparation theorem? Okay, so let's start with formulation. So I'll let f1 up to fk be functions in n+1 variables, real value. Okay, on this guy, on this Rn+1, I'll put the coordinates x1 up to xn and y. Okay, so we have these kinds of functions, and we'll take them to be R sub n definable. These are globally subanalytic functions. Okay, and the theorem is about preparing them, which kind of means writing them in a monomial form. Okay, so as a theorem, so it's due to Pawłuszyński, and independently to Leon, which states that okay, in this setup there exists cylindrical decomposition. Decomposition of Rn+1. So I can write it as a union, even disjoint union of some cylinders. So these are the O-minimal cells. I will not repeat the definition, but if you don't know it, then I will soon define the complex version, and it will also tell you what the real version is. But basically, O-minimal cells. And for every alpha, there is a center. Theta alpha. Okay. So yeah, sorry. So theta alpha is a function from the base Rn to R, such that C alpha does not meet the graph of theta alpha. Soon I'll explain intuitively what is this condition, but okay. There's no intersection between the cell and the graph. Okay, such that for every function j, we can write fj in the form. So it's going to be y, it's the last variable, minus theta alpha to some power lambda j, right, times some function a alpha j of the, sorry, here also alpha and j. Alpha j, a function only of the x variables, okay, and a unit alpha j of, well, of everything, x and y. And this unit, I want it to satisfy u xy minus 1 is less than 1/2 on C alpha. Okay. So I think that's it. there are bigger experts than me here. So if I left out some crucial conditions, feel free to interrupt me. Okay, so basically what it means is that we have any collection of functions, we can find these sets, they're kind of like charts, where the function is a monomial in the first or in the last variable, okay, times, well, something in the previous variables and the unit. It's kind of similar to the singularization where you want to move a divisor to normal crossing. So it means you want to move a function to be a monomial times the unit. And in fact, I mean, if you think about it, you can keep now preparing these guys and write them as well as a monomial times a unit in fewer variables, and eventually you will get some kind of monomial in n variables. And if you do this kind of nested preparation, it will be really similar to what you get from like the singularization theorems. But it's not quite the same. There are subtle differences. So for me, the important difference is that, well, on the one hand, this is not global like the singularization. You are not building some unit like a manifold with a proper map. So that's weaker in a sense. But on the other hand, it is uniform in families. And the way that you see it in this formulation is that we didn't change the order of the coordinates. Okay, so I had these coordinates x1 up to xn and y, and I'm monomializing in the last variable. The last variable is fixed, and I'm monomializing in that. When you are desingularizing in families, I mean, there is no desingularization in families in this sense. You cannot keep your variables separate. You have to make some coordinate transformation that mix up the variables. So when you're trying to work uniformly in families, this is very convenient. Okay, so this is an important theorem. Why is it important? So preparation. So it has many kinds of applications. The one that we were kind of initially interested in is smooth parametrization. So it can be used to construct smooth parametrizations to prove some forms of the Gromov lemma with control of the number of derivatives. And so this is in some work of Klacker, Spiller, and Wilke, and Siegfried van Gile, and other people have worked on these kinds of problems using preparation theorems. But actually there are older and perhaps more significant applications. So it's also used to study integrals. Okay, so when a function is in this nicely prepared form, it's easier to integrate with respect to the last variable, and then you can repeat it and handle multi-dimensional variables. And another thing, I don't know, maybe if it's the first application kind of, is it can be used to study things like model completeness of R and X, for example. So I think maybe this was the initial application, or it can be used to deduce cell decomposition theorems for these structures. So this is what Leon Roland did. So this is not quite this preparation theorem. So this is a subanalytic preparation theorem. But if you want to work in this structure, there is a similar theorem by Leon Roland that extends this to functions definable in R and X. And the subanalytic version is like the base case. And basically everything reduces modulus on syntactic work on the structure of the formula to this base case. So it's quite important also when you're trying to study exponential expansions of a redux of Rn. So each of these I consider kind of significant and interesting for what I will say next. So I mean, I kind of just interested in understanding this theorem better in some explicit sense that I will explain, in order to try to gain something for each of these directions. In some of them we have already done it, like for smooth parametrizations, this kind of strategy work. Also in some cases for studying integrals, and I think basically, I mean, I want to kind of convince you that it's good to understand these preparation theorems better in some sense, and it might help us to gain some insight for these applications. can maybe there are other applications. I don't know. So many people here are better experts than me on this preparation theorem. So if you want to tell me after the talk about other applications that might be interesting, I would be happy to hear it. Okay, so what are my goals in general and in this talk specifically? So one thing that I would like to understand more about this theorem is effectivity. So let me make it like explicit for one example. Like say what do I mean by effectivity? So for example, conjecture. So suppose that now I take my fj's to be just some polynomials pj evaluated on x1 up to xn y and e to the x1, e to the xn, and e to the y. And I'll take this restricted because I want to stay sub-analytic, so I restrict it to 0, 1 to the n plus 1. Okay, so I'm working in the field generated by restricted exponential over the semi-algebraic structure. So I have exponential polynomials, and I can ask about this theorem. So can you suppose you have these nice functions that are very well, we understand a lot about them in terms of counting their zeros or geometric complexity of these kinds of systems of equations of this type. And then I'm asking, so if you apply the theorem, does the number of these C alphas and the complexity of each C alpha depend polynomially on the maximum of the degrees of these polynomials. Okay, complexity I don't want to define. If you attended the Dmitry's talk and you heard about this, so we have some kind of axiomatic notion of complexity called Sharpov minimality, and then you could say what this complexity means. But if you don't know, then let's even just ask about the number of cells. So I would like to know, can you prove it effectively and get a polynomial bound on this number? So I think that if you can do that, probably, okay, it's not completely a theorem, but it may lead to effective Wilkes theorem of the complement. So this theorem of the complement, for those who don't know, it's not about the restricted exponential structure, it's about Rx unrestricted. And it says that if you take a projection of a quantifier-free set and take a complement, it's again a projection of a quantifier-free set. And then you can ask if you can actually do it effectively. So can you say if I had a given formula and I take a complement, then what will be the new formula? How complicated will it be? How many, what is the length of the formula? How many functions should be in there? So I think if you can do that, and then you follow this Lyon-Polan approach for R and X that I mentioned here, then it's very likely that it will lead to an effective version of Wilkes theorem, and I don't know any other way that might lead to an effective version of this theorem. So, I mean, there are other theorems of the complement that have been made effective. For instance, by Selvi and Berarducci and by Andrei Gabrielov, but these are not really about the complement of a sub-exponential set. These are about the complement of a limit set, or, I mean, there's some other types of ways to get a structure. And in these ways, you can prove effective theorems of the complement sometimes, but really Wilkes theorem with a complement of a sub-exponential set, I don't know any effective way to do it. There are a few proofs. There's Wilkes' original proof. There's this proof which is based on preparation theorems, and it is based on some ideas of Russell. And I think that this is the most likely one to, we may be able to make it effective, and this kind of conjecture is the main step towards it. So really you have to kind of look at this original subanalytic theorem and try to make it more effective. Okay, so with that, let me switch to the complex case. Yeah, so I'll start by defining complexes before motivating them. I'll just show you the definition, but I mean, the idea was that we were trying to, well, let me just show the definition first, and then I'll try to motivate it in relation to the preparation field. So what are these complex cells? Complex cells. Let's switch this down. Yeah, so complexes basically, they are some kind of complex analog of the real cells. Okay, so in real cells, you have a definition where a one-dimensional cell is just an interval or a point. And then when you say go to dimension 2, you take a base, which is a cell, like an interval or a point. And then over every point in the base, you put either an interval or a point, and it moves continuously. And the idea was just, okay, let's do the same, but with complex things. So instead of putting real intervals, we put something complex. And the first question is, what exactly do you put? What is this like principal building block? And we have a few more in the complex case than we have. It's not just a point or an interval. So what we consider is either a disk of radius r. Okay, so this is z less than r. Or we can have a puncture disk. Or we can have an annulus. So and we can also have a singleton. Let me edit here. We can also have just 0. So this is like a point, but instead of just allowing intervals, we have like several kinds of. So if you think about the real part of this, the real part of each of these is an interval. Right? So this would be really like a classical interval between R1 and R2. But here you have some, interval between 0 and R. But somehow it's just that in the complex setting, these spaces really are very different. So over the reals, all intervals are the same, but holomorphically over the complex numbers, there's a very different behavior for each of these, and we kind of must incorporate each of them separately into the theory. Okay, so having defined these basic things, let me tell you what is a complex cell. So complex cell. So I'll just say what it is in like length 1 and length 2. So length 1, this is just one of these. One of these guys. So each of these is a complex cell element, a subset of C given by one of these things. Now I'll tell you what it is in length 2, and you can guess the general definition by yourself. So in length 2, so I'll have a cell C. It's going to be something of this form. I'm taking X in C1. So this is my base. It's a cell of length 1, so it's one of these. So X is just going to belong to one of these. And then I'll say that Y belongs to, let's say, D of R of X. Okay, where this R now is a function from the base, C1, to C, holomorphic. So holomorphic function. Okay, so here I took it with D, but of course you could do it. You could say that Y is in a puncture disk here, or you could say Y is in an annulus with so 2 radii that are both holomorphic. Or you could say that Y is in the singleton. Okay, so that is what it is to be a complex cell of length 2. And okay, you can understand how to go to the next length. So it's a very close analog of what we call cells in minimal geometry. But there's some new phenomenon happening here because you are doing everything complex, and because I'm assuming things are holomorphic, then you can talk about some things that don't really make sense in the generality of real geometry. So let me talk a little bit about the most important aspect of this, which is a holomorphic extension. So these cells can be extended. So first of all, let me kind of introduce a little notation here. So if I put a little delta here, I call it a delta extension. It's just a disk which is a bit bigger. I take delta to the -1 times r. So I increase the radius of the disk by delta. And same here, I'll put delta -1. And in the annulus, I'll do a delta here and delta -1 here. So in the case of, let's say I'm doing a half extension, I take delta is equal to 1/2. So if it's an annulus, I'll shrink the inner radius by 2 and I'll expand the outer radius by 2. That is a 1/2 extension. For some historical reasons, we have the inverted delta everywhere. Okay, so I mean, that is the extension of these basic sets. But this still has nothing to do with holomorphic extension. But when you do it for cells, you get into holomorphic continuations. So if I have a cell like this, for example, then the delta extension of this cell is going to be, well, X should live in the delta extension of C1, so I'm extending the base. And then Y should live in this delta extension of Rx. Okay, and here there is hiding a little condition. So before I said that R was a function from C1 to C, but now I extended my base. So this kind of works only if, so it works if this R extends to a holomorphic function R on the extended base. Okay, so there is some condition, you can't always make this extension. You are assuming that all the data that defines your cell is holomorphically continuing to the extension of the base. Okay, and that is the thing that doesn't really make sense in the real case. You can talk about unique holomorphic continuations. So this really brings a lot of extra structure into the picture. Okay, so I want to say what is the main idea behind this? Why do we even consider these holomorphic extensions? Let's try that. Okay, so the main idea behind defining these extensions, is the following. The diameter of the boundary of C inside the extension of C is less than or equal to some constant, depending only on the length and this delta that you took. So I mean, I have to tell you what I mean by this diameter. What is the metric here? And the point is there is some canonical metric that you can use that is intricately connected to the theory of holomorphic functions on these cells. So a brief reminder. So a reminder. So every hyperbolic Riemann surface, so basically every Riemann surface except the things that are uniformized by C or spheres. Okay, so I mean, most Riemann surfaces are hyperbolic, and everything that I will talk about will be hyperbolic. So every hyperbolic Riemann surface admits canonical metric of constant curvature constant curvature -4. You could take -1 here, it's just convenience. Okay, so what is this metric? Basically, it's a theorem of Riemann that every hyperbolic Riemann surface is uniformized by the disk or by the half space. And on this, you have some metric of constant curvature, it's this Poincare metric, and you can push it down. So every hyperbolic Riemann surface is just some quotient of the disk, and the metric from the disk can be pushed down to this quotient. In this way, you get a metric like this on every hyperbolic Riemann surface. And there's a magical property of this metric, which is called the Schwarz-Pick lemma. So Schwarz-Pick. So it states that if F is a holomorphic map between two, if you have a holomorphic map between two hyperbolic Riemann surfaces, it is weakly contracting. So I mean, it's weakly contracting in with this metric. So it's the distance between 2 points can only decrease, or it can stay the same, but it cannot grow. Okay, so it's like Lipschitz with constant 1. Okay, so this is an extremely important lemma. It's kind of the start of geometric function theory. It means that holomorphic functions, they have some intrinsic geometry associated with them. And it's a kind of interplay between this lemma and this fact that makes this theory of complex cells work. So what this means is that if, let's say I have these basic things, so here I can have a disk inside another disk. Okay, so the bigger disk has a canonical metric, and you can ask what is the diameter of the smaller disk inside the bigger disk? Like what is the diameter of D inside D delta? This would be some constant. You can also ask it for the annulus. And for the annulus, it's not true. So if you look at the diameter of such a, A, R1, or let me say R1, R2, inside the metric of the bigger annulus, A delta, R1, R2, this is actually not a constant. This can tend to infinity as R2 divided by R1 tends to infinity. Okay, so it's not true that when you make this extension, the cell inside its extension has a bounded diameter. But what is true is that the boundary has a bounded diameter. So here, for instance, you have this annulus inside this annulus. If I draw this picture with the canonical metric, it looks something like this. So this is the bigger annulus. This is my smaller annulus, like in here somewhere. And this length can grow like log of R2 over R1. But these lengths stay bounded. In fact, they even go to 0 as this tends to infinity. But anyway, this length and this length are bounded. The whole thing is kind of expanding when your annulus degenerates, when this modulus degenerates, but the length of the boundary doesn't degenerate, and this is this is why this thing works. I'm saying that the boundary has a bounded diameter, and that makes kind of everything work. So let me show you just why this is important and how it's connected to preparation theorems, even though it seems something completely different. So let me state one of our lemmas. So it's a joint work with Dynamical. So we call it the monomialization lemma. Monomialization. So monomialization lemma is as follows. So I take F. Say it's defined on an extension, a delta extension of some cell, and it goes into C minus 0. Let's also say it's bounded. not very important, this condition. It's just to avoid some technicalities. But let's say I take a non-vanishing function which is bounded. Okay, then I claim that I can write f of z is going to be some z to the alpha. So this is a monomial, it's a multi-index notation. Z to the alpha times uz, where this uz, let me even say it like this, where log of uz is univalued and bounded. Okay, so I claim that this is quite close to the preparation theorem. It says that if you have a function which is non-vanishing on a cell, then it's basically a monomial times a unit. And this unit is a unit in quite a strong sense. So it's a unit. So first of all, the unit is bounded, even the logarithm is well defined, the logarithm is bounded. Okay, so in particular, the unit itself is bounded away from some multiplicative, bounded away from some constant. So in our approach, the idea, in order to prove this preparation theorem, it would be to cover something with these complex cells in such a way that our function is not vanishing on each of the complex cells, and then automatically the function will be a monomial times unit. It's kind of like, so if you work with smooth functions, let's say you have a function with a 0 at some point, then it doesn't have to be of the form monomial times unit, even in one variable. Right? But if you have a holomorphic function with a 0 at some point, it must be of the form monomial times unit. Right? So and this is a basic feature of holomorphic functions. So this is some kind of extension of that fact. So as soon as, because you have these cells, so you have holomorphic continuation to the whole cell, as soon as you are non-vanishing on this whole holomorphic continuation, you must be a monomial times unit. And let me show you roughly how this is proved and how it connects to this hyperbolic stuff. Okay, so first of all, if I just take fundamental groups, so I have just a fundamental group action corresponding to this F. So this goes from the fundamental group of this to the fundamental group of this. Now, because the cell is basically a product of these basic fibers, it's easy to see that it's isomorphic to Z to the L, or well, maybe even a subgroup of Z to the L where some of the coordinates are 0. If you had something like a disk, or you have this kind of fiber, then there will be no loop for this coordinate. And then here you can even take a subgroup. But in the general case, it will be Z to the L. You will have one loop for every dimension, and this goes to the fundamental group of this, which is Z. So the action of this basically gives you a monomial. So this guy defines our alpha in Z to the L. And by definition, it's such that U of Z, which is F of Z divided by Z to the alpha. So in Z to the alpha, we have the same image in I1, and then when I divide it, then this thing will have a trivial image here. So this guy basically will have no monogamy, so it has a well-defined, has a univariate logarithm. This is just like exercise in the definitions of these fundamental groups. So after you divide by this, you will have no monogamy, and you can take logarithm to be univalent. So that's not the deep part of this theorem. The deep part is that once it's univalent, it will be bounded. And that's not trivial because you should remember that our cells are not compact, right? Our cells, I allow this puncture disk. So they are not compact things, and it can easily, you can imagine that it just goes to 0. And the reason that it can go to 0 is, okay, so let's take F, which is the logarithm of U. So I said it's univalued, so this is some function, holomorphic function. And this function goes from our cell, C delta, to, well, the logarithm of this. And I also said it's bounded. So actually it goes to some half space. Okay, up to normalization, let's say it just goes to this left half space or something. Maybe shifted, it doesn't matter. Okay, so this logarithm goes to the half space. Okay, so this is well defined. And then what I get by Schwarzschild is that the diameter of the F applied to the boundary of C in H is less than some constant in element. Okay, so this is because I said that the boundary has like a bounded length, even bounded diameter in C. And now I'm applying the map F. So Schwarzschild tells me that the map F is only contracting the distances. So if the boundary has, if this has bounded diameter, then after you apply F, diameter can only go down. Okay, now this implies by just the open mapping theorem that diameter of delta of F of C in H is less than such a constant. Okay, that's just because the boundary of the image is contained the image of the boundary. That's the open mapping theorem. So if you take a point which is not on the boundary, it cannot be in the boundary of the image because the map is open. So we have this, and now this implies that the diameter of F of C in H is less than a constant. Okay, so this is some basic geometric fact. If you have a set in the plane, half plane, doesn't matter, some homotopically trivial thing, if you have a set in that and you know the length of the boundary, then you also know the diameter of the set. Right? It's an isoperimetric inequality. So this is isoperimetric inequality. Okay, so eventually we see that the image of this F has a bounded diameter. So in particular, the image is bounded, it cannot go off to infinity. In fact, we have a good estimate for how big it can be. Okay, so when you actually work with this to prove things, then we compute what these constants are. And there's a very good dependence on this delta, and this plays a role in what we do with this theory. But this is basically how the hyperbolic geometry type arguments enter into this stuff. Okay, so I want to show one more lemma of this type that I will not prove, but it's similar, just to show you another flavor of this kind of result. Yeah, so now I'll take it's another lemma. Now I'll take F, which goes from such an extension of some cell into a hyperbolic Riemann surface. So I'll take C minus 0, 1. Okay, so this is a very famous hyperbolic, maybe the simplest hyperbolic Riemann surface. And then if you kind of use something similar to what I did here, a little bit more complicated, you can prove the following. Then either, so one of two things happens. Either F of C is uniformly close to 0 or 1 or infinity. Okay, so these are the three cusps of this hyperbolic Riemann surface, and it could happen that you are very close to one of them. And then, okay, let me tell you the other option, and then you'll see why I reveal these two options. So either this happens or the diameter of F of C inside C minus 0, 1 is bounded by some constant, depending on L and delta. Okay, so I mean, this part is quite close to what you have here. Now you could have just really a puncture disk embedded into a small puncture disk around 0, or a small puncture disk around 1, or a small puncture disk around infinity, and then this doesn't have bounded diameter. Okay, so I mean the cusp, it's a kind of a boundary point of the Riemann surface, and it's infinitely far from any other point on the Riemann surface. So if you have a little puncture disk around the cusp, this thing has infinite diameter. So I kind of really need this. But I'm saying either your whole set lands close to one of these free cusps, or the image is small in the hyperbolic sense. This is what we can prove. And I mean, these types of theorem, they're kind of similar to the little Picard theorem, the great Picard theorem. In fact, they imply the great Picard theorem, for instance. But I mean, it's proved in a very similar way. So it's some kind of generalization to several variables of the kinds of things that you use in proving this Picard theorem. Okay, but I want to get to more explicitly how this relates to preparation of theorems. So let me make probably one more definition. So definition. Yeah. So I have a function. If I have a cell and the function of the cell, holomorphic function of the cell, I'll say that it's compatible with the cell if, well, f is identically 0 or f is non-vanishing. Okay, so for a function to be compatible with the cell, it should either, well, identically vanish, or it should have no zeros. Okay, when it has no zeros, it's this kind of thing that we have in the monomialization. So if a function has no zeros, then it can be monomialized, and you get a monomial times the unit, like in the preparation theorems. So our question will be, okay, let's say I'm given something like a polydisk and some functions inside it. Can I cover it by cells such that each of my functions will be compatible? If each of my functions is compatible, then each of my functions is a monomial times the unit, and then it means that I covered my polydisk with like cells where I have a preparation theorem. So we do have a theorem of this kind. So, so this is a joint work with Dimitri, as I said. So it's the cellular preparation theorem, and it's as follows. So let's say you have functions f1 up to fk on some extension of a cell, a delta extension of a cell into C. Let's say holomorphic and bounded. Again, bounded is not very important, but it's just to avoid essential singularities. Okay, then there exists covering. So I have maps phi j going from some new cells cj into my cell. Okay, so I'm going to, I have maps going from, these are maps that are defined not just on the new cell cj, but on their extension. They go to the extension of my cell. Okay, such that the union of the images of the phi j's, phi j on cj, contains C. Okay, so I'm interested in C. I'm interested in C, but I'm assuming that everything continues analytically a little bit to C delta. And then I'm saying I can find new cells. So my new cells are Cj, their images cover C, and again, everything continues analytically. So actually, these maps continue analytically to a delta extension of Cj. So again, I will have not just cells, but cells with little extensions. And okay, so I have, this is just saying that I have a cover of C. I didn't say anything about the functions yet. So, and if you pull back, so if you do phi j, you pull back fi, this is compatible with Cj. Okay, for every ij. Okay, so it's exactly what I said that we want to do. We are covering C by images of cells in such a way that after you pull back your functions to these cells, they are compatible. So they're going to be, for example, a monomial times a unit. Okay, so this is the kind of analytic version of our theorem, but as I said, we are interested in effectivity. So what we, like, most of the work in our paper was to say that this effective version that I was saying should hold conjecturally holds in the algebraic case. So also, I will not spell it out completely formally, but the effective version, effective I mean with this polynomial control, so really the number of cells is polynomial in the degrees of the function and so on. Effective case holds in the algebraic case. Okay, so if these were all algebraic functions, then I could tell you that the number of these cells depends polynomial in the degrees, and each of the cells has complexity depending polynomial in degrees, and everything that we hope for. Okay, so I will not show you the proof. I will say that this CPT theorem implies the preparation theorem. I mean, this is a globally subanalytic. So basically, when you have a globally subanalytic set, it's roughly a projection of some quantifier free set. Quantifier free set, it's defined by real analytic equations, but you can continue them holomorphically. So you can get to a situation like this where you just have holomorphic functions. And then, well, you need to show that not only do you get this covering on the complex level, but actually that the real parts of the cells cover the real part. So if I had, if say I took this cell to be the polydisk, it's a complex thing, but actually if I now look at my cover, then the real parts of my cells will cover the real part of my polydisk, which is 0, 1 to the end. So, I mean, there's some kind of extra technical work, but basically the idea is as I have explained. So you cover with these cells, you pull back, and on each of them you are already compatible, so you have this monomialization. Okay, but I want to, I will not show the proof, it's a very long and complicated proof, but I want to give just some kind of intuitive ideas for how the proof works and how these how these lemmas play a role in this proof. So let me just show you with a picture what happens in dimension 1. So what is the theorem in dimension 1? So in dimension 1, let's say my cell C is, say, something like a disk. So I have a disk, and it's living inside a little bit bigger disk, like let's say twice bigger disk. So this is C, and this is C delta. And now I have some function on C, and I want to cover the set by something that's compatible with the function. So in this case, because it's one-dimensional, basically the function has some zeros, and I'm trying to cover my disk by disks that will be compatible. So they should either, they shouldn't contain one of the red points. It could be a puncture disk with the center in a red point. So you could have a puncture disk like this, or you could have some other disks, whatever you want. But the condition is that the other disks shouldn't meet the red points. Okay, I said compatible means either you are identically vanishing or you are non-vanishing. Okay, so there will be puncture disks around the red points, there will be other disks, but I want to know that even when I extend the disk times 2, it will still be non-vanishing. Okay, I mean, I was saying that like these maps are actually defined on the delta extension. Okay, so I want to know that each of the disks that I have here, even after I make them twice bigger, they are still non-vanishing. Okay, and this is kind of crucial. It's because we had always these extensions, that's why we had bounded diameters, that's why we got this monomialization. So you need to have this extension feature. But I claim that, okay, the first thing is, can't you just do it with disks always? So why are we even bothering? Okay, I explained that we need puncture disks because otherwise you're just not allowed to touch the red points. So the only way you are going to do something around the red point is if you allow puncture disks. But why not just disks and puncture disks? Like in this picture, you can do it with disks and puncture disks. Clock. Okay, so what happens in the case of what happens? Why do we need annuli at all? So this happens when you have this kind of picture. So let's say I have my cell, and let's say I have two red points that are quite close here. And let's say another one here. So if you're going to start, let's say you're not using annuli, then you can only put disks. And around these disks, you can only put very small disks, right? Because you want disks such that when you make them twice bigger, they will still not touch the other point. Okay, so you can make a little disk around this guy, very little puncture disk, and a little puncture disk around this guy. And then you have to start putting many more disks here. Okay, you will need more, and the closer these two red points are, the more disks you have to put. It's a matter of easy, like elementary geometry. So, and then it wouldn't be good. We want to know that regardless of how these points are situated, there is such a covering, and the number of cells that we need eventually is going to be polynomial in the number of points. So definitely it will not work like this. So what we actually should do is we should put one annulus that surrounds both of these guys. Now, if these guys are very close, then this annulus will, like the inner circle will shrink a lot. So it will be like a very long annulus. And this annulus is like a magnifying glass. So now, outside of this annulus, we will do a puncture disk, and we will, I don't know, just here it will be easy. And then inside of the annulus, you get a similar picture to what you had before, but now you have the two red points, you kind of magnified in, now they're not so close together, and inside the annulus you can repeat this picture. So you put puncture disk here, and you cover the rest with puncture. So now the points are not colliding, so you don't have this issue. But of course it can happen in a more complicated way. Maybe after you zoomed in, you notice that actually there's another point here very close, and you are still in trouble. So you'll need another annulus to separate these 2 points. So, like in general, depending on how your points are geometrically situated, you will need a certain number of annuli. And it's not a tough exercise to show that actually you can always do it with a polynomial number of disks and annuli. So if it's an exercise you can give a student, just you have a disk, you have a collection of n points, show that you can always cover it with disks and annuli satisfying this property, that when you extend them times 2, they still don't meet each other. So that's not the hard part. So the hard part is what happens when you're going to dimension 2. So when you're going to dimension 2, you have this kind of picture, but it's moving with a parameter. Okay, so you have, let's say I'm in dimension 2, so I have some kind of, my points become curves. Something complicated like this. And now for every fiber, I have a configuration of points. Right, so here I see 3 points, and here there maybe 2 of them came close. And so for every choice of X, you will see a different picture. And what we are trying to do is to draw these kinds of pictures, but you want it to vary holomorphically with the base, right? Because eventually we are trying, if we are dealing with such a 2-dimensional picture, then the theorem says that you find 2-dimensional cells that cover everything. So we need to kind of be able to cover this picture with a 2-dimensional cell. So it means we are making some choice of these disks and annuli in the fiber, and then also this choice is moving holomorphically over the base. And so you can see from these pictures that it's quite, so maybe this kind of picture looks relatively steady. So if the red points don't move much, then you will be able to, let's say I drew this kind of picture, now I move a little bit, the red points move a little bit, the picture will still work. But if you have a picture like this, it becomes more complicated because here you had 2 points. When they move a little bit, it's after you magnify, it changes things a lot. Right, so here I actually had, after I magnified, I saw that I have another 2 points that are even closer. But for this point to say move here, in the original scale, it's a very small motion. So like when the points are close together, even changing a little bit will really change the configuration of the cell decomposition. So that is the problem. The problem is how can you divide the base into cells such that over each cell you will be able to do this thing uniformly. And kind of the question is so given some points, given a collection of points, what are the numbers associated with this one? What are some coordinates on the space of points that once these coordinates don't move much, I know that I have a fixed configuration of cells. So I want to be able to say that there is a certain coordinates on the space of tuples such that if I know that none of these coordinates move much, then I can just make a constant type of cover, it will work uniformly. And these examples show that you can't, it can't be just checking how much every point moves separately. You have to see things like the relative differences between the points. And what I claim is that actually the coordinates that you really need, so the coordinates that you need in order to control the configuration of these cell decompositions are exactly the yi minus yj divided by yi minus yk for every I, j, and k. So these are the points. It's like y1, y2, y3. So this is kind of measuring the relative distances. Okay, this is the distance between y1, yi and yj, and this is the distance between yi and yk. If you know all of these distances and you know that all of them don't move much, then you will be able to make a fixed combinatorial structure for this cell decomposition. And these coordinates are well known in algebraic geometry. They are basically the coordinates of the Thornton-McPherson compactification. Thornton-McPherson. So which is a very important compactification on these configuration spaces of endpoints. So it's a well-known phenomenon in this study of Thornton-McPherson compactifications that you only need triples. So you should, for every 3 points, you should see how it behaves, and that's enough. You don't need some kind of information that encodes the relation between 4 points. So if you know for every 3 tuple of points, you know this ratio of the distances, you get a very good compactification, and this translates into being able to make this subdivision into cells uniformly. And okay, how does this connect to all of this stuff? I claim that this is exactly this lemma. Okay, so suppose that I do have a cell and I have n points over it. So I have like a cell here and I have a certain number of points over every fiber. And now I look at this ratio. So every 2 points are different. I can assume that they are different. I can throw out the discriminant locus where 2 points collide. It means that this thing cannot vanish. And it also means that this thing cannot vanish. So this function cannot take the value 0 and it cannot take the value infinity. And it also cannot take the value 1, because if it took the value 1, then yj would be equal to yk. Okay, so all of these functions, they are actually functions. So these are all functions from the base C. So like here, let's say I had C a base and this is a fiber. So they're all functions from C into C minus 0, 1. And then this lemma tells us that they don't move a lot. In fact, we can make this constant very small by increasing delta. So if we choose delta right, we will know that these functions hardly move. And when they hardly move, we can make this choice of how we subdivide the fiber. We can make it uniformly over the entire base. And it's really a matter of like a delicate asymptotics. So checking, how this metric on C01 behaves. And I mean, how uniformly close you are in the other case. And it all works out. I mean, it's the asymptotics of the hyperbolic metric exactly allow you to make this subdivision work with a polynomial number of sets. So this is how we get like this effective version in the algebraic case. It's because you can just analyze everything in terms of this metric, and it just happens to work that the bounds that you get from this lemma are exactly what you need for this subdivision. And well, the hope is that you can now do this instead of working with algebraic things. You will work with, let's say, exponential polynomials or some Sharpe or minima structure, and you get the same effective CPT, and this will give you an effective subanalytic preparation theorem. And then you can hopefully get at some of these applications that I mentioned at the beginning. So I see I'm 2 minutes over time. Sorry, I'll finish.
Thank you. Other questions or comments?
I have a question, not very important, but why not? So say you have a fixed area of these points and you want to have this cell decomposition. Do you know how to do it? It's clear that like for every selection of locations, you will have a different combinatorics, like how many magnifying glasses you need and how many just balls you need, discs you need. But like for a specific one, for a given one, is there an effective way to understand what's the best decomposition?
I'm not sure about the best, but we have kind of an algorithm. We have some kind of formula that, given all of these numbers, tells you what decomposition to choose. You kind of subdivide. So you choose one point as a center, then you subdivide all the other ones. You order them according to their distance from the center. You cluster them, and you do something. But I mean, this thing that you do, it will work for a certain value of the coordinates and also for nearby values. So if all these values don't change much, then this thing will keep working. And then you have to prove that really you can like subdivide the base in such a way that it will not change. So your algorithm will keep working in the same way. So you don't get some like discontinuous jump in your configuration.
Okay, great, thank you. That's also an interesting question, like how to do this clustering. So yeah, okay, thanks.
Yeah, well, you can read this paper. Yeah. It's somewhere in there.
Are there any other questions? If not, let's then speak again.
Okay, thank you. I'll switch back to my laptop camera.
See you tomorrow.
Yeah. Okay. Yeah. Thanks very much.
Yes. Thank you, Gal. So,
sure.
Thank you again. So the next lecture and the next session is tomorrow at 9. It will be in this room, and all the lectures of the morning session will be in person in the room. And there is, as today, there will be one lecture in the afternoon, which will be online and again screened as it was today. Thank you very much.
Gal is